Good morning, good afternoon, good evening, folks. Depending on where you're logging in from today, one of those will sound just about right to you. Welcome back to another great episode of our weekly Best Practices webinar series with 7SIGNAL. I see a lot of you have logged in here early. Thank you for doing that as always. If you'd like to, let us know where you're logging in from. If you are in the office today, if you are working remotely from home. I myself am back in our Cleveland headquarters office, and we are joined today by special guest Keith Parsons. Where are you joining us from today, Keith?
I'm in Moses Lake, Washington. A little on-the-road trip, not business-oriented, it's more personal, but here in Moses Lake.
Awesome. Well, we're happy to have you back. I think the last time you were with us was our virtual user group in February. Is that correct?
Yes, okay. Probably. You would know. That's the kind of thing we track.
That's true. Well, we're happy to have you back as always. And we are also joined.
Was that the one you were playing your guitar on?
It was.
Yeah.
It was. Thanks for
Okay,
remembering.
then definitely memorable experience, yeah.
Well, thanks, Keith. Happy to have you. Also joined by Jim Vada, as always, in Cincinnati. How are you today, Jim?
Very good. Just patiently awaiting the arrival of the brood 10 cicadas down here.
Lovely. Any day now.
Any day now.
Any day
Yep.
now. Well, good luck with that. I see a lot of you dropping in here. Let's see where you're logging in from. We have Karsten joining us from the office in Germany. Thank you for joining us. We have Germund joining us from Norway. Thank you, Germund, as always. Let's see, we have Flavien joining us from home in France. Thank you for tuning in. And I see a lot more of you dropping in. Please continue to do so, and we'll go ahead and get started here. So we are 7SIGNAL, the leader in wireless experience monitoring, and just like every webinar, we will give a brief history on who we are as 7SIGNAL before we dive into today's topic. A really interesting, highly relevant topic today, update on 6 gigahertz in global regulatory domains. And as I mentioned, we are joined by special guest Keith Parsons and Jim Vada, and I'm Kelsey Rizzuto, the marketing specialist here at 7SIGNAL. Really excited to dive into this today, and throughout the presentation, if any of you have any questions for Keith or Jim, feel free to drop them in the questions panel, and we will cover them during Q&A at the end. So a couple of announcements here. We do partner with CWNP for every single one of our webinars, so if you're pursuing a certification, you are eligible for continued learning credits by attending today. So if you'd like a certificate, just drop us a note, and we can easily email a PDF to you per request. We also send out a newsletter every other Wednesday, the Digital Experience newsletter from 7SIGNAL. So if you are not currently receiving that newsletter and would like to, again, go ahead and drop us a note, and we will make sure you are on that list to receive. We also host a product tour every single Friday at 12 noon Eastern. You can go ahead and register at that link there, go.7signal.com/tour, and that link will be provided in the chat here if you'd like to join us this week for any updates on Mobileye and Sapphire Eye. We also post, after every webinar, our recording and the slides to our Twitter account, so if you're on Twitter, go ahead and give us a follow, and that will be up there later this afternoon. But if you're not, no worries. All of you will be receiving a follow-up email with today's recording and the presentation slides as well. And with the recording, we also post all of our previous webinars to our YouTube channel as well. So you can go ahead and watch today's presentation later today, or you can go ahead and watch some previous topics we've covered. So a little background, we were established in 2007, and we were headquartered in Helsinki, Finland, and we're now headquartered in Cleveland, Ohio. We've hit a lot of major milestones along the way that we're incredibly proud of, such as the 1 billion data points that we're analyzing daily, in addition to the 5 million devices that we're monitoring daily as well. And with that, we also have 15 patents, which goes to show that the technology you see from us at 7SIGNAL, you're only going to see from us at 7SIGNAL. So to give you a little background as to what makes us so different, if you look at your typical enterprise LAN infrastructure here on the right, you've probably got great tools, great technologies, giving you really useful feedback, such as your Riverbed, Cisco, Aruba, AppNeta, and more. But we live in a different space, picking up where they leave off, not only giving you that infrastructure view, but that view into the personal user experience. And we'll start here first with Mobileye. Mobileye, as I said, gives you that visibility into the user experience and can be installed on the individual devices themselves as a software agent, such as your laptops, your mobile phones, your scanners, workstation on wheels, and more. And it can also be installed on any Mac OS, Linux, Android, or Windows device as well. And with Mobileye, a lot of us here are working from home and will continue to do so at least a few days out of the work week. With Mobileye, you can get that user experience perspective from your external home networks. So it's incredibly critical to stay connected to your work no matter where you're logging in from, and that visibility is highly relevant. So with Mobileye, we also have Sapphire Eye, which are sensors for service level quality and RF visibility, giving you that full perspective as to what's occurring in your network that you just can't find anywhere else. All right, thanks for letting me run through our history of 7SIGNAL. Before we begin and hand it over to Keith, we are going to launch a couple of trivia questions here today. We have 3, so we will start with this first one. All right, Keith and Jim, can you see this question?
Mm-hmm.
Okay. How do clients find access points in 6 gigahertz? See a lot of you dropping these answers in. Give you some varied answers here. I'll give you a couple more seconds to see what we get here. All right, we're going to go ahead and close this. All right, Keith, how did we do here?
Great. 40% of the people got it right. So they've been listening and learning to know how 6 gigs is going to work. I do favor A because that's what we're used to in the past. The problem with in doing the same thing we did in the past in 6 gig is we just have too many channels and it takes too long. So the B and D are 2 methods that are possible for us to use, and we'll talk about those a little later in the presentation.
Awesome. Well, thank you, Keith, and thank you to everyone for answering that first question here. We're going to launch our second question. All right. How many 20 megahertz channels are available in the US for 6 gigahertz? Several of you are dropping in.
I'll
give you guys a couple more seconds.
1,200 divided by 20, very roughly.
Oh, you're too many hints there, Jim.
All right, here. Let's see. How did we do on this one?
Fantastic. And the trick on this one was US, because US is different than other countries. And yes, Jim gave away the secret that it's 1,200 divided by 20 is about 60.
All right. Thanks for the hint, Jim, and thanks for everyone for answering that question. We have one last question here. Let's see how we do here. Okay. Is 6 gigahertz going to change everything in Wi-Fi design? All right. Give you guys a few more seconds. And we're going to close this. All right. How did we do on this last question?
Good job, Sam Clements. Your answer, it depends, is the winner.
Awesome.
But I can see the yes and the no both have validity, because in some ways it will change everything. In other ways, it will change nothing at all. But for most of it, it's going to be in the it depends category, depending on what our clients' needs are, what our requirements can be. So it is very much like what we've done so far, and in other ways, quite different.
All right. Thank you, Keith. Thanks to everyone for those trivia questions. And with that, I'm going to go ahead and pass our controls over here to Keith. And while he gets set up, I'll let Jim give a little introduction to our guest.
Thanks, Kelsey, and we're really pleased to have Keith Parsons with us again here today. If you don't know who Keith is, he's a world-renowned wireless networking engineer. He's a trainer. He's a podcaster. And he also puts on the best Wi-Fi conference there is, the Wireless LAN Professionals Conference. Hoping to be back in person one day with you, Keith. So
it's coming soon.
Welcome to the webinar.
Well, thanks. So I was asked to talk a little bit about Wi-Fi 6E and where 6 gigahertz is today. So put together some slides and give us some things to talk through. Under introductions, I didn't even put a slide there. I've been on 7SIGNAL before, you know me, and if you don't, track me down. Keith R. Parsons on Twitter or www.pros.com. So to start out with, we're going to start with the 6 gig allocation charts. I built these probably over a year ago for my own learning. Admittedly, I'm not a graphic designer. I did them in Excel. And the reason I like doing such things in Excel is because if there's a formula of how the channels are designed, then I can replicate that with Excel spreadsheets. A lot of people, you know, if the only tool you have is a hammer, everything looks like a nail. For me, my tool of choice is a spreadsheet. So yeah, that's where I went. So first one I'm going to show you is the full chart, but it's a little too small on the screen. So I've sent Kelsey a PDF of it so you can take your own and print it out and use it however you like. So I'll show you the full one just to give you a little understanding. And then I'm going to zoom in on the details to see what's included in this graphic. And you can see there's a lot of extra information. I'm a trainer at heart, and so I try to put as much educational information as you can, and I'll cover those. And then we'll look a little bit at the US low power and the US standard power. There's another version for US that's not quite legal. They haven't ratified it yet, so I didn't show that one. It's on the main screen, but I'm not going to drill in. And then we'll talk a little bit about the ETSI or the EU version for a second. So moving on, here's the full chart. Lots of stuff there. The top three are the FCC, and then the low power, indoor, standard power, and the one that's the third one down is what is currently under review, and that will allow us to have very low power. And then at the very bottom on the left is the ETSI, and they only have 500 megahertz versus the US is running 12. A bit later in the presentation, we'll talk about what different countries are approving or reviewing today. So rather than just look at this full chart, really hard to zoom in and see, I zoomed in for us. So here's the zoom in version. It's just the same chart. I just went in the upper left-hand corner. There are, across the top, where it says low indoor power, if you go a little to the right, it says 5925, and that's a little 20 megahertz band that's kind of a guard band setting in there. And then you can see across the top in vertical text, there's the actual frequency. The center frequencies are used down below where it says center frequency. And then the 20, 40, 80, 160, 320 are the channel numbers. If you note on the 20 megahertz line, all the way on the left, there's 59 of those. That was one of our questions earlier today. There's also, and since again, this is in the spreadsheet, I can make that be a count. And so it actually counts the numbers that are across the thing, and we can change it and it would automatically update. On that same 20 megahertz line, there's some that are bold. The bold ones are also highlighted down below in the thing that says preferred scanning channels, the PCFC. Those are the channels that can be used under one of the methods to find an available channel. Rather than scan all 59 channels, you only have to scan every fourth channel. This has only been updated in the last little bit because of some issues some people found, and then they moved these. They used to be 117, and now it starts with 5. It's shifted over. It was a kind of little esoteric reason. Across the top, you also see a big thing that says wavelength 5.1 centimeters, which equals 2 inches, and that's for that 5945 frequency, and that's a calculation based on how radio waves have a wavelength divided by the speed of light kind of thing. Then down below in red is what the free space loss is. At each of those channels, that's the number in dB loss of free space loss. And note that it's growing along the way. And also this is a calculation, so it looks at what the center frequency is and then does the calculation to find out what free space loss is. Again, back at the top where it says low power indoor, on the right side, it also has how loud we can talk, which is different than we had in the past. In the past, we had some limit that was based on SNR, and if we went to a wider channel, We had more noise, so our net effect was we got to transmit lower. That's been around since, well, 2 decades or more. In 6 gigahertz, they changed how this is calculated, and what we end up is a net EIRP of 18 dBm. Oh, I need to change that M to a lowercase, sorry. But that net dBm means that if we go to a wider channel, we actually can adjust and change our transmit power to make sure we deliver the same amount of energy on the receive end. Even if we do have higher noise values, the new regulations allow us to transmit a little higher, so we net the same amount along the way. And this is also calculated in dBm per megahertz. And so depending on how many megahertz wider channels are, we get to transmit it at different powers. And so that's the detail of what's in this chart. If we look at the US 6 gigahertz, and on this slide, I broke them into 2 halves. They actually go on the end of each other, but that meta is zooming a little too close. So I just kind of cut on the right side at the end of Uni 5, and then put Uni 6, 7, and 8 on the bottom. Again, this is for low power, and this is legal today, and all these channels are available to us. You can see the channel numbers, and as we go from a 20 to a 40, obviously we have fewer channels. We go to an 80, we have fewer channels. We got from 59 all the way down to 14. And today, these look like a huge amount of available spectrum, and it is 1,200 megahertz of spectrum, 1.2 gigahertz of spectrum available for us. It's going to be fantastic. We had some Twitter threads and discussions a while back, and actually had a private discussion online last week with Chuck Lukaczewski and Lee Badman and Peter McKenzie, talking about what's going to be the new standard as we move forward in 6 gigahertz. Are we going to stay with the 20s? Are we going to 40s or 80s? And Chuck said something like 80 is a new 40. Well, I still believe the same rule holds true. I like hanging onto a rule and finding the rule and just keeping with it. And the rule for me is use the widest channel you can until you can't. But how do you know when you can't? Well, that's when you get co-channel interference. So depending on the antennas you have, the AP locations, and the wall attenuation you have, your different buildings might run into scenarios where you need to go to 20s in order to minimize co-channel interference. For me, I would rather have 2 20s than 2 40s that can see each other, because for me, co-channel interference is the killer of Wi-Fi. It's the one where we go from having one person or 1 AP's worth of clients sharing the frequency to having 2 AP's worth of clients sharing the same frequency. Even though you got a wider frequency, they still have to contend for time. And later in this presentation, we'll look and again go back and see how much that contention process takes from our airtime. So in the US, we have all these channels. Yay, wonderful. This is for low power, indoor. There's some rules about this. It's like you can't have an external antenna. Anyway, that's on other things we can talk about with 6 gig. And here's one, and I zoomed in just a little bit on the standard power. And you'll note that any place and down below, so the 20s are still available to us. But when we get to 40s, because Uni 6 doesn't under standard power, we can't spread and cross over one of these boundaries between Uni 6 and Uni 7. So anything that would have crossed Uni 6 and 7 is now not available to us. So if you look over right between Uni 6 and 7, there's one that has a 118 as a channel number, or I think it's, sorry, 116, and it has a line cross through it, and it's empty because it crosses those boundaries, and so we don't have access to it in standard power. There's rules about this, and the net effect is if you go to the standard power, and then we have some AFC issues as well, we'll have to have fewer channels to deal with. So yeah, we still have the 20s, but if we go to that standard power, there's a lot of our 40s and 80s and definitely way fewer 160s to play with. So we have to look at these and go, oh, is it really worth that? Right now, I don't know of anyone building and shipping standard power devices, but this has been FCC approved. The next one down, I don't even have a slide for, is the very low power, and the FCC still has that under review. Now for ETSI, or the EU, they have this smaller subset, only 500 megahertz, and I say only 500 megahertz, I'm sorry, they only have 24 20 meg channels. That's more than they have in 5 gig today. So yeah, it's still fantastic. We still love it. I know some of our friends across the ocean are a little jealous that we have a little more in the US, but they do have 500 megahertz. It's a huge amount. And later when we talk about different regulatory domains, you can see not all regulatory domains have picked the same horse to bet on. Some of them want different things. Now, there are some reasons for this. In different regulatory domains, there are incumbents, and they can't easily give up and take this frequency away from an incumbent that they already have. So there's legitimate reasons for it. And even if I was in the EU, hey, that's a lot more channels you have today. Now, what it might be is if you're in the EU, you might end up with more 20s because you need that channel separation. You don't have as many 40s to play with. Now, let's talk about different countries. Now, each country has a regulatory domain, and to keep this from being overly US-centric or EU-centric, it's just in alphabetical order. And so the EU shows up here. The UK is a little different, kind of Brexit stuff. And you can see they have the same low power, very low power, and standard power. And in each of those, they have slightly different. There's either the 1200 megahertz team 1200, or team 500. And again, that's because of the rest of the things in the regulatory domain. Some have also looked into the very low power, and they have a different power setting. You can use very low power, but at a unique number. 17 dBm or 14 dBm is usually the place they go. If you look down at the second to the bottom line, we have the US, and we have ours at the very low end of our power that those charts show. But under very low power, we're still under advisement. That little FNPRM is just a term for that they're not done yet. It's still under review. And then in the standard power, we only have Uni 5 and 7, and so anything that's in between we can't use, which is why we lose those channels. But it has a transmit power of 36 dBm. So yeah, we can yell pretty loud. So these are the countries as of the 1st of April that had already went through and agreed that this is what they want, and they published it. But there are other countries, Egypt, India, Japan, Oman, Qatar, and Taiwan, that are very close to coming on board too. So we should have a lot of countries, but realize that a lot of them, as this starts to flow downhill, will pick up more and more, and we'll get there. So if you're in a country, I don't know, Canada or perhaps Australia, where your country hasn't jumped on board yet, just wait. It will come. It is coming. And as you can see here, it's not just a US thing anymore. A lot of the world has come on board. Well, let's talk about MCS, my favorite subject. This is an old MCS chart, still valid, but it's 807N and 807AC. And you can follow along, and it shows for each MCS, there's a modulation, there's a coding scheme, there's a channel width. Inside the channel width, there is a short guard interval or a long guard interval, and then you have a minimum SSR and a minimum RSSI, and you can calculate this. And we've been using this for, probably a decade now. But I want to show this gets a little more complex as we step up into OFDM with 807AX. And this is just the OFDM one. There's another one for OFDM-A, which is even more complex. And instead of just going up to 7 like N or 9 like AC, and AX, our MCS index goes up to 11 per spatial stream. What we did is we added a 1024 QAM. 256 QAM at times can be difficult to attain. 1024, that's way up there. Now, I'm telling you this as a warning. A lot of times, marketing people like to do all of their quotes at 8 spatial streams, 160 megahertz wide channels with 1024 QAM. Yeah, that's fantastic. The chances of all those happening, pretty low. But what you have to also notice is the difference between the old MCS index, which there was only 7 or 9, and we only had 3 channels, and there's only short or long guard. That's still a lot of choices. But in AX, it gets even more complex. We have 3 different types of guard intervals. We have 4 different types of channel widths, and we have up to 11 MCSs. So again, getting more and more complex, more and more details. And this doesn't even count when we get into the RU side. Now, I prepped all of that so we could talk a little bit about spatial streams and channel widths and look at what's going to be realistic in the world versus what is not quite so realistic in the world. So let me come over here and if we look at the spatial streams, and I put these into three categories, I just called them good, better, best. If you are running a below 64 QAM, your Wi-Fi is having a difficulty at some level. For each transmission that's going to go out, the transmitter, it could be the AP, it could be the client, is going to make a decision on which modulation scheme to use based on their history and how well it worked in the past, and a whole bunch of other algorithms that are proprietary. But if you're running below 64 QAM, say 16 QAM, there is a problem. Your client can, any client today can, and APs can, do better than 16 QAM. They can do 64 QAM or up to 256. So good is if I can maintain an MCS that supports 64 QAM or better, I'm having a fairly decent time with the RF. I'm not congested, I'm not dropping frames, I don't have a high retry rate. So just that MCS index alone will tell me the health of the Wi-Fi at that point in time. So I put this good as an example, and I highlighted two spatial streams in bold, the 344, as a fairly decent target. If I have an iPad, a lot of phones today are two spatial streams, most laptops are two spatial streams. That's kind of our sweet spot. If we have a good network, we're running 64 QAM, and we should be getting about 344, and that would be great. We love that, especially when you consider Netflix only needs 4 meg, and we're getting 344. This is almost 100 times better than what we demand. This would be fantastic. And I picked 40 megahertz, because if in 5 gig we had 40 megahertz, we can, and about half. I was watching a presentation by Chuck Lukaczewski on Aruba Atmosphere presentation they did just a couple weeks ago. Highly recommend you go and watch that. You can go log on for free to the Aruba Atmosphere 2021 site, go to Airheads, and you can find Chuck's presentation. A lot of great information there. And he showed some charts showing between Aruba and Cisco, both 40 megahertz channels and 5 gig are about half of all the channels out there, which I'm assuming if they did a good job on design, you could minimize your CCI and still go with 40 megahertz channels. If you can't, use 20. So that's what I just highlighted that one. And now if we look below in the yellow, in a US region, it's one of the Team 1200 versus Team 500, there's 29 of those, which means in 6 gig, we should easily be able to have 29 spread between our 40 megahertz channels and not have co-channel interference. That's way better than we have today. Yes. Now, if we wanted to look better and say, maybe in our new design, we have APs that are close enough to our customers, close enough to the clients, that we can actually get a 256 QAM consistently. Now, I found it very difficult to design for 256 QAM because you have to be fairly close to pull that off. And then when you get that close, then your APs are too close, and then you get co-channel interference. So I don't plan on 256 QAM, but if you had it, you can see it jumps from 344 up to 459. That's pretty decent. And then if you go over and look at the 160 column, and that's the one where I said, yeah, right, I don't think we're gonna, I think it's possible to have 1024 QAM, highly, highly unlikely that many of your clients are gonna be in that space. So we're probably gonna be between 340 and 450 in our per user net experience. And we all know that if you wanna test Wi-Fi and test it for throughput, the fastest you're ever going to get is when you put one AP and one client and there's nothing else on the channel. Because everything else you add, additional clients, are going to have to share that same bandwidth. Okay? So this was just a preface to come back. We're going to come back to this very same slide in just a minute after we talk about a few other things. So let's talk about this. Probably a year ago or so, I gave this presentation for 7SIGNAL about in order for a single frame to get transmitted on the air, it has to go through all these steps: an AFES, a contention window, a preamble, RTS, CTS, CIFS, preamble, CTS, CIFS, preamble, header, payload, all of that to get to the payload. The payload is the only thing we care about. And in this graphic, the payloads are in blue. Well, let's look a little closer about this. There are spreadsheets, both one from Aruba and Germund. Thank you, Germund. I use your spreadsheet all the time to calculate how much airtime is being used with different configurations. Remember the MCS chart had all those different things and there were so many possible choices? Well, each of those choices is for modulation, encoding, and channel width. Well, they each result in a different airtime. So we use a calculator to go through and show those. So let's look at a couple of the answers of these calculators. If you look at a frame, and this happens to be just a little 90-byte TCP ACK frame. Now, we know in internet we're sending TCPs all the time, TCP data, but there's also coming back a TCP ACK. And so for TCP transmission, it could be up to half of all of our transmissions are this size. And for a transmission of 90 bytes, look at all the airtime being used to deliver that single little slice of blue. It's a very small slice of airtime. And so when we're talking about, oh, we're going at 450 megabits or 1,000 megabits, whatever the number is, it's all of these. And then we have to calculate, well, what's actually going to go over the wire? Yeah, it's just the blue. Let's look at some others. Here's one, and these are these say they're an airtime comparison, but the two I picked up are exactly the same. All I'm trying to show is when you put these two in there, it's the blue, the payload. And this is a 512 byte frame, and it's running around 12%. So if all that airtime we're using up, only 12% is going to come back and be a frame that gets converted into Ethernet that gets put on the wire. Changing our calculator, and this is using Guillermo's calculator, what's the difference in airtime when we go from a 20 megahertz to an 80 megahertz channel? Now, we think of that as a huge change, and and especially our customers, they love going, give me wide, give me fast. But from an airtime basis, in this picture, it's the green is the only part that's changed. Yes, we went to a wider channel, and our payload went faster, but all the other parts were exactly the same. Same is true for spatial streams. If, again, green is the payload, and that's the part we care about, when we go from one spatial stream to two spatial streams, yes, we pick up twice the speed of the data frame. All the rest of the airtime is still taking as much time as it was. So let's look back now at that same graphic and come back and say, oh, between the good, better, and best, even if we hit something, let's say miraculously in the future, my next iPhone has 4 spatial streams and I'm getting 256 QAM and I'm running an 80 megahertz channel and I get nearly 2 megabits throughput. That's 1922 on this chart. 11% of that is still below the threshold for gigabit Ethernet. So I went through all of this just to let you know, I personally like running multi-gig switches. Why would you buy an old switch today if you could buy a new switch? And your APs need more PoE, they need all sorts of things. I'm not anti 5 or 2.5 or 10 gig switch ports. It's just not caused because you have to have one because of Wi-Fi. So when you're looking at the Wi-Fi, even in the 6 gig, the 6E Wi-Fi, realize the chances of you running 1024 QAM are near 0. 256 QAM, maybe some percentage of your clients will be within that zone. Great. If you choose 80 megahertz channels, clients, I doubt they're going to be more than 2 spatial streams for a long time because of battery life. You're still not pushing more than a gig Ethernet traffic. So that was my setup to get to that screen. Now, we talked about this a little bit earlier. In 6 gig, because we have those 59 channels, how and what's the technique going to be used to find an AP? Today, a lot of our clients will scan. They'll scan 1, 2, 3, 4, 5, 6, or they'll scan off channel, they're talking, and they'll send a data frame back up and scan 1 or 2 channels along the way. We have a lot of channels in 2, 4, and 5. And it takes, even if you only dwell 1/10 of a second, it takes like 3 seconds, 2.5 to 3 seconds to scan all our current channels. Well, if we added all the 6 gig channels and to scan those, it might be anywhere from 5 to 6 seconds long just to go to find an AP. So that's why we need to come up with a discovery process. And they did a couple of methods. One is called in-band, and that's when you have a 6 gig client and you're going to look in 6 gig to find APs. There's 3 versions of them: unsolicited probes, active scans, and this FILS system. I'm not going to get into the details, just realize there's some ways to do it inside of 6 gig. But they also made it that if you have an out-of-bound discovery, you can go to an AP in 5 gig and query it and get this reduced neighbor report that already tells you, oh, here is where the APs are in this area on this channel. There's another way that you could have multiple BSSIDs in your beacons, so you could just go and hear one beacon and it tells you about its neighbors as well. So realize the 802.11 committees are looking into this, and they've come up with solutions and ways to help speed up that discovery process. Okay, I'm done with the first part. Now let's go and look at some of your questions. Jim, I'll relinquish control and you can carry on with the Q&A for a second.
Yeah, happy to, and thanks, Keith. And I want to welcome anybody in the audience that has a question for Keith to drop it in the Q&A panel. I got a question here from Nikita, and she asks, minus 47 dBm at 1 meter seems like a huge drop. A couple of meters from an AP and the signal strength may not be usable.
That is a fantastic question. And so that's one of the reasons I've added that to that chart. That's only for the first meter. And the way free space loss works is the first meter what I didn't show you was how we got to that 1 meter is we went, what happens at the first centimeter? And then at 2 centimeters and 4 centimeters and 16 centimeters. So what it is this a logarithmic curve. And 1 meter just happens to be a place we chose on that curve, just to be easy. But now the easy part is every time you double the distance, you get 1/4 or a minus 6 dB. So let's say at 1 meter, you're minus, I'll just pick an easy number because of the math, you're at minus 50. At 2 meters, you're going to be at minus 56. At 4 meters, you're going to add another 6, you'll be at minus 62. Got to do math in my head live, that's hard. And so you can just calculate these in your head. So if we just give you the one trigger point at 1 meter, everything else is just adding 6 every time you double the distance. 2, 4, 8, 16, 32, you can add those on. So depending on which frequency you're in, 2.4 gig, it's close to 40 dB at 1 meter. And so there is about a 6 dB difference between 6 gig and 2.4 gig at any one distance. But if you look at those two charts, the cool part about them is they match. It's the same curve, they just have a different starting point. So the actual curves are the same. At any distance, if you're 6 dB different between 2.4 and 6 gig, at 20 meters, you're still 6 dB different. It's a consistent loss across the board. Did that help, Nikita? I hope so.
I think so. Thanks, Keith. Question from Brian. He says, do you know anything about the 6 gigahertz outdoor mobile AP spec and how it's going? I think he's asking about the very
Standard
low power. Well, he says mobile AP.
Yeah.
So
the mobile would be the very low.
Yeah.
In the US, we're not quite there yet. So I don't want to comment on something that I know is not finished. Some other countries have that. If you look back at the chart I had, you can download the PDF and see some countries have a very low power already available, but I think it's only a handful, and those have a very low power. I think between 14 dBm and 17 dBm is their max.
Vincent says, wouldn't the overall aggregate throughput of the access point justify M-gig switching?
Thank you. You must work for a vendor. You like selling them. No. And the answer is it depends. And you can, and I have, and lots of people have, push an AP, especially a tri-radio AP, to over a gig throughput. You can make it do it today. It's just really, really rare. Because the only way you can make it today is you max out every one of your radios with the perfect 256 QAM with 3 spatial streams, and you can contrive a situation to make it happen. If you look at any of the marketing literature, they always grab 4 spatial stream 160s. And that's why I gave you that little chart that I actually showed up twice. In the real world, the good, better, best, we're usually in the good. We may get into the better, but I doubt we'll ever hit the best. So just look at those numbers and go, oh, what are we getting? And even if you triple it, it may not be there. I'm not saying don't buy an M-Gig, just don't believe the hype that says you have to have it because of Wi-Fi. There's a lot of reasons to have good M-Gig. I would love to have it in every one of my ports. It's just not required because we actually don't hit those numbers. And even if we did, even if we hit the 2 gigabit Wi-Fi with a 4 spatial stream at 256 QAM and you're only 6 meters away from your AP, and then you have to go and take out all of the airtime overhead to get down to the 11% that actually goes across the wire. Yeah, sorry, you just poked my trigger button.
Yeah, Keith, and my take on that too is it such a bad thing to just realize that our bottleneck used to be the Wi-Fi link, and if we still have a gigabit switch, well, now the bottleneck is that gigabit link.
Maybe,
but
it could be.
What are the business requirements that are driving a need for more than 1 gigabit of throughput for anything? They're just not there yet.
Well, I think part of it is, and we went through this cycle maybe 10 years ago as well, when we're trying to push 1 gig, because you can easily make Wi-Fi overrun 100 meg.
Mm-hmm.
And so and what happened was, in the past, we would have an access layer that the switch was designed that each switch was an aggregator. So it might have 2400 meg ports and needed 2 gig uplink because not everyone talked at the same time. And then we took those very same switches and we would put an AP on the end of one of those 100 meg ports. And the AP itself is an aggregator. And so then our switches became the bottleneck because we put an aggregator on the outside. Well, now our APs or aggregators are now 3-channel and going faster, but we have gig ports everywhere. Now I can easily see a 24-port switch that has APs on its edge overrunning its gig port up, like guaranteed that's going to happen. So, and the other is, when do you do it? If you're in the middle of a switch cycle today, of course buy M-Gig, but don't go and say we can't go to Wi-Fi 6E until we have M-Gig everywhere. You can run and then catch it up. So they're 2 different cycles. They are linked, and I like them, and I think they're useful, and I wouldn't ever dissuade someone from not buying one. I just don't like the story that you have to buy it because of Wi-Fi.
I don't either. And there's kind of a cascading effect. Oh, I want to have M-Gig at the edge. Oh, suddenly I need maybe to upgrade my core and distro, and my WAN and internet links, and it's more power hungry.
On your VAR.
Yes.
Now the power is the one I really support. Definitely don't chintz out on your PoE. It's the PoE, because one of the things we've seen for the last 10 years is, as APs improve, they have more power draw. And if you don't have the power budget on your PoE, APs will downgrade themselves dynamically. They will still work, and then someone's going to have to go troubleshoot Wi-Fi because it's not a Wi-Fi problem, it was a PoE problem, but the AP downgraded, and then that caused a Wi-Fi issue, and it was all because you didn't have enough switch power.
Yep. Maybe one last question, Kelsey, and we'll end, I think, on a positive note with this one. Keith, Mark asks us, me too, do DFS issues disappear in 6 gigahertz?
What DFS issues are we talking about? No. What do you mean DFS issues? We don't have any DFS issues. Yes, because we don't have radar incumbents in there, and part of the negotiation for the 6 gig, well, we do have incumbents. They are there, and as part of, there's a lot of point-to-points that are in there, and so the reason what we're stuck first with just low power and very low power is that we wanted to be nice to all the incumbents. That was part of how we got approval. It's also part of the reason why in Europe they didn't get a bigger chunk of spectrum, because there's more incumbents in that area and they have a little less control. So we do have incumbents, but we found a different way to solve it. And so we have this automatic frequency coordination function when we move to standard power that goes out and asks the database and says, is anybody here? Can I now transmit this thing? And so it's a more orchestrated, organized version than, oh, I hear you on my channel, I'm gonna run away and hide. So DFS was a solution that worked without coordination. Each individual AP was responsible for not causing pain to an incumbent. And so the FCCs around the world made that really hard and fast. And so that's why the DFS issues happen, is someone has to jump off and it leaves a hole, and what does the client do? We don't have any of that in 6 gig. They found a different solution that's a little more orchestrated and organized. And on the good part, for most of the stuff we'll be putting in the short term, we'll be using low power, and low power doesn't have any of those restrictions because they figure, it doesn't exceed the size of the building too much. And if you don't allow them to put in external antennas, which by the way is a rule, you can't have external antennas, you can't even have adapters, the chances of it inside of a building 6 gigahertz bothering an incumbent are near zero.
All right, great. I think that wraps it up. Thanks, Keith.
All right.
Thanks for having me on. Glad to come in and talk about it.
All right. That is all we have time for today. Again, thank you, Keith, for joining us. We love having you back, and we had a lot of great questions and engagement from the audience today. So thanks for assisting with that Q&A, Jim. So we hope to have you join the 7SIGNAL team again. But for today, thanks for giving us 49 minutes out of your workday, and we hope to see you soon. Thanks, Keith. Thanks, Jim.